Sir, I'm Snigdha. I'm here to present the case study on visual analysis of global satellite distribution. In the next 7 minutes, I'll walk you through four stages: how we prepared and cleaned our data, the core tools and modules behind the analysis, a quick look at our datasets and how they were merged, and finally, the insights from five key questions, each answered through visualizations. By the end, I hope you'll see how satellite deployments, once the domain of superpowers, are now global, data driven, and rapidly evolving. Pre-processing. Let's begin with pre-processing. We built a robust data loader to handle messy real-world files where CSV or Excel it automatically tries encoding like UTF-8 or Latin 1, check separators like commas or semicolons. If fails, even resorts manual praising. Once the data is loaded, satellite data processor takes over. It standardizes columns, renaming mass into launch mass. It clears numeric values, ensuring consistency. It categorizes satellites. For example, com becomes communication. Launch vehicles are grouped and orbitals are classified into LEO, MEO, and GEO. We even derive new fields like launch decade and inclination category, low inclination if 30 degrees or below, high if 60 and above. Outliers are trimmed with quantile methods, leaving us with a clean, reliable data to work with. Key modules: Pandas and NumPy form the backbone for data handling and calculations. Matplotlib and Seaborn gives us rich static plots. Plotly brings interactive subplots. SkiPy adds density contours, and scikit-learn support regression analysis. All this wrapped in a Google Colab environment, warning suppressed for clarity. In short, a modular reproducible pipeline. Part 3: Merging. The USC satellite database contains over 5,000 satellites launched between 1957 and 2025, with details such as satellite name, launch mass, inclination, and more. The space mission datasets adds 2,000 records with launch location, date, and country. We merge the two using left join, aligning launch date with mission date and mapping vehicles to launch sites. The result is undefined and dataset are clean data ready for analysis. Insights: the five questions. Question 1: Are high inclination satellites lighter or heavier? A scatter plot with density contours tells us in LEO higher inclination satellites are about 25 kgs lighter. In MEO, lower inclination satellites tend to be heavier. In GEO, lower inclination satellites weigh on average 765 kgs more. This suggests orbital mechanics our mission needs strongly shape satellite mass. Question number 2: How have satellites' purposes shifted? Stacked charts reveal that striking patterns. In 1970s, military satellites searched during the Cold War. In 2000s, Earth observed peak thick climate monitoring and security after 9/11. In 2010s, communication dominated, fueled by Starlink and mega constellations. Communications grew from 50% of the launches in 1970s to nearly 90% in 2010s. Question number 3: Is there a nonlinear power mass relationship? On a log-log scatter, we find for most orbits, powerless scales linearly with mass. But in GEO, sometimes unique happens. Beyond a threshold about 3084 kgs, the slope changes dramatically, meaning heavy geosatellites demand disproportionality more power, the critical for planning large communication satellites. Question number 4: Which launch vehicles dominate over time? Bar charts and line plots show Soyuz and Proton ruled in 1980s to early 2000s. In 2010s, Falcon rockets exploited in popularity, accounting for 99% of LEO launches and growing over 1800%. Meanwhile, Long March from China steadily expanded, signaling a multipolar space race. We can clearly identify eras of dominance. Question number 5. Do launch sites cluster geographically? A heat map shows clustering. Russia leads with 127.8 launches, followed by USA with 911 and Kazakhstan with 719. Hotspot emerged at Baikonur Cosmodrome and US sites like Cap Canaveral. These latitudes reflect the sweet spots for orbital mechanisms. Our analysis reveals three broad shifts. Satellites are becoming lighter and more efficient, especially at inclinations. Communication satellites driven by mega constellations are reshaping orbital landscapes. Launching dynamics are no longer dominance by one nation. SpaceX and Long March mark a new exploring era. The data highlights are not just technical evaluations but also a geopolitical strategy for governments, companies, and researchers. Understanding these patterns is crucial for shaping our future and space policies. Thank you for listening, sir.